With this video, we're starting a new chapter and a new topic, and we're going to begin our study of acids and bases. Although I think you'll find that this chapter relies very heavily on the previous chapter on equilibrium. And we're going to start by giving a new definition of acids and bases compared to what you would have learned in Chem 1, and it's a broader definition, and they're called Bronsted Lowry acids and bases. So the first definition that most people learn for acids and bases is what's called the Arrhenius definition. And so with this definition, an acid is a substance that produces H plus ions in aqueous solution, and a base is a substance that produces OH minus ions in aqueous solution. So HCl is a common acid, and so when that dissolves in water, that dissociates into H plus ions and chloride ions. And so we consider that an Arrhenius acid because it produces H plus ions in solution. On the other hand, sodium hydroxide is a common base, and sodium hydroxide is ionic. So if I take solid sodium hydroxide and dissolve that in water, it will dissociate into sodium ions and hydroxide ions. So again, it's considered an Arrhenius base because it produces OH minus ions in aqueous solution. But it turns out for chemistry, this definition is a little restrictive, and so we want to broaden that a little bit, which is what the topic of this video is. So before we get to this new, broader definition, we have to talk a little bit about H plus ions. It turns out these don't actually exist in solution. When that HCl dissociates that we saw on the last slide, those H plus ions actually associate themselves, they combine with water molecules to make the H3O plus ion. And this is called a hydronium ion. So in solution, we don't really form H plus. What we form instead are these H3O plus ions or hydronium ions. Now, chemists are often lazy, and so we often use H plus and H3O plus interchangeably, but H3O plus is the more correct way to think about what we actually have in solution. Now, for a lot of chemistry, the Arrhenius definition is a little bit too restrictive. It would be better and easier if we had a broader definition for acids and bases. And so one broader definition of acids and bases is called the Bronsted Lowry definition. And in this definition, acids donate H plus and bases accept H plus. So to see what we're talking about, let's use HCl as an example of an acid again. And so if I take HCl and let that react with water, what's going to happen is the HCl is going to donate this H plus to the water molecule. And when that happens, the HCl is not only going to lose an H, but because it's losing an H plus, it's also going to become more negative because it's losing the hydrogen and the positive charge. And so what that's going to leave behind is the Cl minus. And then it's donating that H plus to the water. And so in this case, the water becomes H3O, but it's not just donating an H, it's donating an H plus. And so we don't just get H3O, but we get H3O plus. And so in the Bronsted Lowry definition of acids and bases, HCl is acting like an acid because it's donating its proton, its H plus, to something else, in this case, a water. All right, an example of a Bronsted Lowry base is ammonia. And it might be less obvious why this is a base. It doesn't have any OH in it, doesn't have any hydroxides. But let's see what happens when we combine ammonia with water. Now, I'm going to use equilibrium arrows here. I'm not going to get into that too much now, but we'll definitely talk about it later in the chapter. But I just wanted to be formally correct here. So if ammonia is acting like a base, it's going to accept an H plus from the water, or you can think about it as stealing an H plus from the water. And so on the product side, what was the NH3 is going to pick up an H, so it's going to be NH4, But it's not just picking up an H, it's an H plus that's being transferred. And so we're going to get NH4 plus. And then when the water loses an H plus, it's going to have OH left behind. But because it lost the positive charge as well as the hydrogen, it's going to become OH minus. And so in this case, ammonia is acting like a base because it accepted the proton from the water molecule. Now, I should say, we don't have to forget about the Arrhenius definition. Anything that we would have classified as an acid under the Arrhenius definition would also classify as an acid under the Bronsted Lowry definition. And the same thing for bases. Anything that's an Arrhenius base is also a Bronsted Lowry base. But it does allow us to classify additional things, new compounds that wouldn't classify as acids and bases under the Arrhenius definition, but they will classify as acids and bases under the Bronsted Lowry definition. In the Bronsted Lowry definition of acids and bases, there are many compounds that can act as both acids and bases. It just depends on what other things they're being combined with. And a classic example of that is water. And actually, the two reactions that we wrote on the last slide demonstrate this. Right? In this first reaction, the HCl is acting like an acid, and it's donating the proton to water, but we can also think about the water is accepting the proton. So it's acting like a base in this reaction. And then when it reacted with ammonia, ammonia was acting like a base, and so it was accepting the proton from water. So in this case, the water was acting like an acid. So the water could both act like a base and like an acid. And so we would say that water is amphoteric. And so how we would know which one it's going to act as depend on what things it's combined with. If we react it with something that is a stronger acid than water is, then it'll act like a base. Or if we react it with something that is a stronger base than water is, it'll act like an acid. So it depends on what it's combined with, which an acid or a base is going to behave as. A really important concept that comes up when we talk about Bronsted Lowry acids and bases is the idea of conjugate acid-base pairs. And so these are pairs of species where one's going to be in the reactant side and one's going to be on the product side, where these compounds differ only in the presence or absence of a proton, an H+. Right? So the two conjugate pairs in this reaction are H2S, and then its pair is HS-, right? Those compounds only differ in that the H2S has an extra H+ compared to the HS-, or we can think of it as the HS- has one less H+ than the H2S. Or the other pair here is the ammonia, NH3, and the ammonium ion, NH4+. And so whenever we have a Bronsted Lowry acid-base reaction, the base accepts the proton, right? The NH3 is accepting or stealing the proton from the H2S, so it gains that H+ and it becomes NH4+. And so the partner of the base is called a conjugate acid. And then when the acid donates its proton to the base, it becomes the conjugate base. And so we would say H2S is the acid, and the HS- is its conjugate base. And so it's also interesting to look at this from an equilibrium perspective and the fact that these reactions can run in either direction. Right? If we imagine the reaction running in the forward direction, the H2S is acting like an acid because it's donating the proton to the NH3. But if we were to imagine running the reaction in reverse, so if we imagine these as being the reactants, and then they're being converted into these things, right? It's the NH4+ that's donating the proton to the HS-. And so it's acting like an acid. So conjugate acids, if we think about the reverse reaction, would act like an acid. In conjugate bases, in this case, if we go in the other direction, the HS- would be accepting a proton from the NH4+, and so conjugate bases do act like bases. And so what's the acid and the base, and what's the conjugate acid and what's the conjugate base, is just kind of a matter of perspective. I could have written this reaction flipped, where I put these on the reactant side and then put these things over on the product side, and then I would have called this the acid and this the base, and then this would have been the conjugate acid and this would have been the conjugate base. So an acid is always paired with a conjugate base. A bases pair is always the conjugate acid. All right, so let's look at an example. So we want to look at this chemical reaction, and we want to identify the acid, the base, the conjugate acid, and the conjugate base. Now, by convention, the acid and base will always be on the reactant side, and the conjugate acid, conjugate base will be on the product side. So let me recommend, pause the video and try and make the identifications, and then restart it and see if your predictions match mine. All right, so let's see how you did. So I want to identify the pairs, the conjugate pairs, so the things that differ by just the presence of a proton or not. So I think in this case, I have the HSO3 minus and the H2SO3 as one pair, and then the HBr and the Br minus as another. And when I look at this reaction, right, the HBr has lost a proton, and the HSO3 minus has gained one, right? So the proton went from the HBr to the HSO3. So the HBr is donating the proton, so that's my acid. So that makes the HSO3 minus the base, and so then the base turns into the conjugate acid. So the H2SO3 is the conjugate acid, and then the Br minus is the conjugate base. All right, so here's another way that we might ask questions related to conjugate acids and bases. So in this problem, they're asking for what is the conjugate base of HNO3? So if I'm looking for the conjugate base, then I'm saying HNO3 is acting like an acid. And so if HNO3 is acting like an acid, then that means it's donating an H+. And so to find the conjugate base of anything, take away an H+. So it loses an H, and then also because of the charge, it'll become one more negative. And so since this thing is neutral, the conjugate base is going to be one less hydrogen, so it's going to be NO3, and then it's also going to become one more negative, because it's not just losing the H, it's losing the H+. So the conjugate base of HNO3 is going to be NO3 minus. Or if they're asking for the conjugate acid, then they're saying this thing is acting like a base, and a base is a proton acceptor. So if this accepts a proton, it's going to gain one more hydrogen, and then it's also going to become one more positive, because it's not just gaining an H, it's gaining an H+. And so it's going to go from negative, and it adds +1, it's going to go to neutral. So when I add the hydrogen, it's going to become H2CO3, and it goes from a -1 to a 0 charge. And so that's the conjugate acid of HCO3 minus. All right, so let's finish up by writing some chemical reactions involving Bronsted Lowry acids and bases. So in this first example, I want to write the reaction for H2PO4 minus acting like a base when it reacts with HBr. So I'll write down my two reagents. I've got H2PO4 minus, and it's reacting with HBr. All right, but in this case, they're saying it acts, we want to write the equation for acting like a base. So bases accept protons. So that means it's going to accept or steal the proton from HBr. And so in this case, the H2PO4 minus is going to act like a base. And so that means the HBr has to act like an acid and donate the proton. So my products are going to be H3PO4. So it gained an H and it became one more positive. And then the HBr is going to lose that H and become more negative, and so it's going to become Br minus. All right, and then in our last example, similar thing. So I've got the same starting material, but now I want to write the reaction for H2PO4 acting like an acid. All right, so in the previous one, it acted like a base. Now it's acting like an acid. So H2PO4 minus is an example of another substance that is amphoteric. Depending on what I combine it with, it can act as either an acid or a base. So I'll write down my reagents. So I've got H2PO4 minus. It's going to react with NH3. Only now we want it to act like an acid. And so it's going to donate a proton. And so the H is going to be transferred from the HPO4 minus to the NH3. And so if it loses an H, it's going to become HPO4. But not only does it lose the H, but it becomes more negative. So it's going to be HPO4 2 minus. And then the ammonia, the NH3, since the H2PO4 is acting like an acid, that's going to act like a base. So it's going to accept the proton. So we'll add one H and it'll become one more positive, and so then I get NH4+. All right, and so then this was the last example in this video.